very interesting question at Slack, which asked, what is the difference between the models or these function-based methods? We use functions, so we have predictors which take the feature vector as input and output a predicted label. What is the relation of these methods, these machine learning methods, to other types of methods which are known under the name Bayesian networks or hidden Markov models? The difference is that I try in this course to use only models, and it's just models. So this here is a particular class of models, and in this course we use another particular class of models. These here are probabilistic or Bayesian models. So they use probability theory. They interpret the data, so the data set that you observe, features and labels, they interpret the data as realizations of random variables, and then assume some particular form of probability distribution underlying this data. So we have a probability distribution which tells us what is the probability that we should have observed exactly this feature and this label. So there's a probability distribution involved. And we will actually see today that for soft clustering methods, this is quite useful to use such a probabilistic modeling. However, for most of the course, I try to avoid probabilistic models because you can illustrate the main ideas of machine learning without any notion of probability or random variables. Within our course, a model basically amounts to specifying a hypothesis space. So this is a model. And in the end, all machine learning methods amount to fitting a model to data. There's nothing else behind any machine learning method than fitting a model to data. How do we fit the hypothesis space to data? Well, we pick the particular hypothesis out of this which minimizes the empirical risk over some training data. So this here means fit the hypothesis, a generic hypothesis out of the hypothesis space, for example a polynomial, to the data X, which is a bunch of Bitcoin and Ethereum closing prices, or a bunch of redness and greenness values of snapshots. That's data. In probabilistic modeling, we try to fit, it's the same game, or the same principle, we fit the probabilistic model that we have, a probability distribution, to data. How do we do this? Does anybody of you know a principled approach to fit a probabilistic model to data? Sorry? Using Bayesian theorem, yes? Or did anybody hear of maximum likelihood? Yes. So maximum likelihood is nothing but fitting a model, and a model means here a set of different probability distributions which are characterized by some weight vector or parameter. For example, this might be a Gaussian distribution. Don't worry if you don't understand the shortcut. It's not crucial for this lecture today. So this means a Gaussian probability distribution with mean W and some covariance matrix C. And we tune a parameter vector to best fit the data. And how do we fit the data? We maximize the probability of observing the data points given the weight vector. And this is, turns out this is equivalent to empirical risk minimization if we define the risk as minus logarithm of the probability. So this here, this probability or this likelihood function can be used to define a loss function. And then maximum likelihood becomes empirical risk minimization. So these two types of models are basically using different names and notations for the same thing. It's about fitting a model to data. So I wanted to answer this question because I find it very relevant to point you out that in this course we mainly leave out the specifics of probabilistic models. There are at least 2 courses I'm aware of in our department. One is called Bayesian data analysis, and the other one is called Machine Learning Advanced Probabilistic Models. And these 2 courses, I think each of them is a 5-credit course, they focus on how you fit such probabilistic models to data. And you will see a lot of similar tools there. In particular, there might come up a gradient descent algorithm at some point, because you just tune a weight vector or a parameter vector to fit the data optimally. And you can do this using gradient descent if this distribution is sufficiently smooth, for example. Okay. Any questions regarding modeling paradigms? Yeah. Which of them is the consuming? Time consuming. Well, so the question is, how do we know which models are the fastest to implement? And I cannot answer this because this depends highly on your hardware. So if all you have at your disposal is a spreadsheet calculator, then you might not go for deep neural networks. Yeah, so there is a trade-off between the time complexity or the computational time complexity and how well a hypothesis fits data. The basic principle is the larger this hypothesis space is, the more options you have to fit your data. However, the larger the hypothesis space is, the larger is the space you have to search over, so the more time you need. And we have seen this already for a simple class of hypothesis spaces, which is given by polynomial regression. The higher the degree is of the polynomial, the more degrees of freedom you have to perfectly fit your data. However, you run soon into numerical problems, because in order to fit the data, you need to invert matrices which are nearly to singular, which requires a lot of computational power. So already here you see an intrinsic trade-off of learning accuracy and computational resource requirement. The more accuracy you want to have, the more you need to invest. And invest means really money, because you pay for computation time, for example, on cloud services. Yeah, but this is out of scope of this lecture. This is subject to my current research. Okay, any other questions? Good. So, yeah, I would say we have now a break till 11, and then I will discuss some of the most widely used unsupervised learning methods, which don't need any labels of the data. They just learn from the intrinsic structure of data sets. These methods are called clustering methods, and we will look at, I would say, the 2 dominant approaches for 2 different flavors of clustering. So one is k-means for hard clustering, and then soft clustering using Gaussian mixture models. And here, Gaussian mixture models is a probabilistic model, and we will see here how useful it can be to interpret your data as random variables. Yeah, okay, let's see at 11. So, hey. exception, yeah. Yes, midnight, yeah. But a few minutes before midnight. For me, it's important that it's on Friday, not on the weekend. Yeah, yeah, for everybody. For everybody, of course.
My question is pretty easy. I'm an exchange student here for a semester, and I'm searching for like topics.
Yeah.
This kind of stuff.
Yeah.
What should I do? Should I directly send an email to some students? I know that it's
Yeah.
like probabilistic machine learning.
Yeah.
This one is not Bayesian and stuff. But do I need to add like previous knowledge about this? Because otherwise,
You just ping them.
okay. And how does it work with the supervisor? Should it be like someone like professor like you or some assistant at the lower level to the supervisor? I mean, not in general. In general, how does it work? So, yeah.
Okay, so in 5 minutes?